Hello, good morning, Year 11. So let's get started again today for your science lesson. So 1 to 5 on the mini whiteboard. And you need to match up these definitions to the correct key term. So you can pause the video for the next few minutes and work on those. And then remember as well, you need to click the register. So you need to click that you're here so we can mark you off on our registers. Okay, so let's go through the answers then. So for the first one, thermal decomposition of long alkanes into shorter alkanes and alkenes. So I'm not sure why it says thermal decomposition there, and it is my mistake. It should say cracking. So ignore what it says in purple. I don't know why I've typed that, to be honest. Number 2 then, a distance a car travels once the brakes have been applied to stop the car. So this is your braking distance. So this can be affected by like the road conditions. Are they icy or slippery? Are you driving on gravel or a nice smooth tarmac? Things like that. The point through which the point through which the weight of an object can be taken to act is the centre of mass. Number 4, joule is the unit of work and energy. So we've just done the work lesson yesterday. And then an object returns to its original length after being stretched. That's elastic deformation, which we'll learn more about today. So today is all about that concept of elasticity. So how far can you stretch something? Can it go back to its original shape? And what happens if it doesn't? Okay, so we're learning about that concept today. So our learning objectives then are to give examples of forces involved in stretching, bending, or compressing an object. Explain why, to change the shape of an object, you would need to apply more than one force. And then describe the difference between elastic deformation and inelastic deformation caused by stretching forces. Okay, so what we have here are some examples of where you might stretch an object. So with the catapult, you are stretching the rubber or elastic bands. Okay, and there's a lot of potential energy in those bands. When you let the catapult go, that energy is then transferred into kinetic energy, and it will then send that object flying through the air. So you have a big store of potential energy in a stretched object. Okay, you can compress an object by applying two balanced forces in opposite directions. So if you look at the pictures of the hand compressing the spring, you can see how the green arrows show that you've got two forces acting in opposite directions to compress the spring. When you're stretching the spring, you're holding one end in a fixed position and you're pulling the other end away. So you're just applying that one force then. With the can, you're crumpling it, you're compressing it by squeezing it from both sides, from squashing it from both sides. And then with the beams, you can see that when the beam is supported at two ends, like the middle diagram, that if you put compression, so you're squashing something down and there's a load on top of it, so it could be that objects have been placed on top of it, that there is also in the opposite direction tension held in that beam, in that material, and they're acting in opposite directions. Again, when you've got the cantilevered beam, so only supported at one end, you've again got two forces on one side and one on the other. So you've got multiple forces acting in opposite directions, and that is having an effect on the object. Okay, so we need to look at this concept that for elasticity, you would need multiple forces to be applied to cause an object to change shape. So if we took this can, and let's just say it was a regular can, it hadn't been squashed yet, and you only tried to squash it from one side, so you haven't got both sides, you're only trying to go from one side, what would then happen if you just use one hand to try and squash one side? Would it squash? Would it move? Would it stay still? What would it do? So explain what would happen if only one force was applied to the side of the can. What would you visually see? Okay, would it squash? Would it compress? So tell me that in your answer. What would it do? So I think you need to give yourself a few minutes to pause the video and tell me about this. Okay, so here is what would happen. So we can review this in purple pen. If only one force was applied to one side of the can would not change shape. It can only compress if two balanced forces are applied. When only one force is applied to one side, the can may start to move from a stationary position. So if you've only got one hand on it and you're trying to squash it, it won't squash, it will move. It will change its direction or it will change its speed, but it will not change its shape. So for an object to change shape, you would need two forces, often applied in opposite directions, okay, to change the shape of an object. So then thinking about these two definitions, elastic deformation and inelastic. So elastic is an object that returns to its original length after it's been stretched. So if you took a hairband, for example, and you're pulling it, when you let it go, does it spring back to its original size? And we can tell if we measure the original size and then stretch it and then it goes back to that original size, we know. But if you take a spring and you stretch it and stretch it and stretch it, there comes a point at where you've actually gone past the sort of point of elasticity, and it will not go back to its original length when you remove that force. And so we will be investigating that in future lessons. And this is what it looks like on a graph. So this is a force extension graph, and the straight diagonal line shows a linear relationship. So the diagonal part shows a linear relationship where the object being stretched still could return to its original length. So it's got elastic deformation. So it's temporarily changed, but it can go back to its original length. Where we've got the dot that says limit of proportionality, that's the point at where your object will no longer return to its original length. And at that point, it becomes inelastic deformation. So you've now stretched it too far, and when you remove the force, it will not go back to its original, length or size. Okay, what I want you to do now is pause the video and have a read of this. And what we're essentially saying here is that different objects are obviously made of all different materials and they've got different elastic limits. So that point on the graph, that limit of proportionality, can vary for different materials. And we notice on the graph that it goes from being that linear relationship to non-linear at the point it starts to curve and bend round. So what I would like you to do is I would like you to draw a sketch of this graph, and then I've also put some additional links on Google Classroom. So the Seneca links, the BBC Bite-Size links, those ones, and I think the Blue Science Guy as well. And what I want you to do is put this diagram in the middle of a page and then annotate around the edge, and I'll show you an example in a moment. So I think this will take you, 5 to 7 minutes to do this. So pause the video. And here is one I made earlier. So I've just sketched the graph in the middle. And what I'm going to ask you to do is pause the video at this point, and can you see what you've got in relation to mine? And then can you just add more information if any of it needs adding to yours? So have you got the fact that the first part of the graph is linear, the second part is non-linear? So pause the video, please. Right, some exam questions then. So the spring inside the Newton meter behaves elastically. What happens to the length of the spring when the object is removed from the Newton meter? So will the spring get longer, will the spring get shorter, or will the spring stay the same length? So I think you can just say this in your head, or you can write it on a mini whiteboard or in your book, it's up to you. We'll count to 5. And we have this one, the spring gets shorter. So you remove the force that you're applying to that spring and it will bounce back, it will get shorter. Okay, here's another one then. The diagram below shows pairs of forces acting on different objects. In each case, describe what happens when the forces are increased. Then describe what happens when the forces are removed. So you've got a thin strip of plasticine. You've got two pulling forces acting in opposite directions. So if you increase those pulling forces, what will happen to that thin strip of plasticine? So plasticine is a bit like Play-Doh, if you've not heard of that. or a little bit like blue tack in the fact that it can be stretchy. And then if you remove those pulling forces completely, what would then happen? So this would actually be worth 4 marks. So you should pause your video for 4 minutes. And let's look at the answer. So for the first one, we need to say that our plasticine will stretch. And we could then actually say that at some point it may snap. Okay. When the forces are removed, the spring will compress. Now in the mark scheme, it says OWTTE. That stands for, or words to that effect. If you said compressed and instead of that word you said squashed, okay, so that's pretty much the only word you can say instead of compressed. So the spring was squashed. And then also for the second mark, returns to the original length or shape. Okay, so that's how we get our 4 marks for those. So OWTTE stands for, or words to that effect. So what is a different word for compress? So we could say squash. Okay, so that's the end of our lesson. I look forward to seeing your work on Google Classroom, or you can email it to us directly. It's really nice to see what you're doing at home. We do miss teaching you guys, and we are looking forward to having you back in school. So thank you very much.